Hello, dear listener, and welcome to this quiet space, where we can gently turn our thoughts to the grandest story of all, the story of everything, the tale of our very cosmos, known to us as the Big Bang. As you settle into your comfort, perhaps feeling the soft embrace of your blanket or the quiet stillness of the night, let us embark on a journey, not through physical space in this moment, but through the boundless realms of cosmic time and profound scientific understanding. Imagine, if you will, a time before time, a place before space, a moment so utterly fundamental that our everyday language struggles to grasp it. The Big Bang isn't truly an explosion in space, but rather the astonishing expansion of space itself, bringing with it all that we know: matter, energy, time, and the very dimensions we inhabit. It describes, in the most profound scientific terms we currently possess, how our universe unfurled from an initial state of unimaginable density and incredible heat. Picture something so compressed, so fervent, that all the vastness you see when you gaze at the night sky was once contained within a point smaller than an atom. It's a concept that stretches the very limits of our imagination, inviting us into a state of awe and wonder. From this primordial crucible, this incredibly compact and superheated essence, the universe began its magnificent expansion. This wasn't a slow, gentle blossoming, but an incredibly rapid and dynamic unfolding, governed by the very laws of physics that we now strive to comprehend. Our most sophisticated cosmological models, built upon the bedrock of the Big Bang concept, have allowed us to decipher a remarkable range of phenomena that paint this grand picture. Think for a moment about the elements that compose you, me, and everything around us. The hydrogen in the water we drink, the helium in the balloons of childhood memories, and even traces of lithium, these are the universe's earliest children. The Big Bang models beautifully explain the precise abundance of these light elements observed throughout the cosmos. It tells us that these fundamental building blocks were forged in the fiery crucible of the very early universe, a testament to its initial heat and density, cooling just enough for these simple nuclei to form before the universe became too diffuse. It's a cosmic recipe, inscribed across the vastness of space, and one that aligns perfectly with our observations. Then, there is the ancient whisper of the universe itself, the cosmic microwave background, or CMB radiation. Imagine the afterglow of that initial fiery state, stretched and cooled over billions of years, now detectable as a faint hum of microwaves permeating all directions of the sky. This isn't just a faint signal, it's a direct echo, a photographic snapshot of the universe when it was a mere 380,000 years old, transitioning from an opaque plasma to a transparent gas, allowing light to travel freely for the first time. The CMB is perhaps one of the most compelling pieces of evidence, a profound cosmic lullaby that reminds us of our ancient origins, a nearly perfect blackbody spectrum, uniform in every direction, just as the Big Bang predicts. And what about the galaxies, those majestic islands of stars that dot the cosmic ocean? When we look out into the night, we notice something remarkable. Distant galaxies are moving away from us, and the farther they are, the faster they recede. This phenomenon, known as the redshift of galaxies, is like the stretching of sound waves from a receding siren, but for light. The light from these faraway galaxies is shifted towards the red end of the spectrum, indicating that the space between us and them is expanding, carrying them further away. It's not that the galaxies themselves are necessarily hurtling through space, but rather that the very fabric of space between us is stretching, much like dots on an inflating balloon. This redshift is a direct, observable signatu of an expanding universe, a concept utterly central to the Big Bang. Furthermore, the Big Bang helps us understand the large-scale structure of the universe, the intricate cosmic web of galaxies, galaxy clusters, and vast empty voids, resembling a colossal, luminous sponge. This structure, too, emerged from the subtle initial fluctuations in that primordial soup, amplified by gravity over cosmic eons. Yet, as with any grand tapestry, there are knots and threads that require closer examination. Early on, cosmologists pondered the remarkable uniformity of our universe, questions known as the horizon problem and the flatness problem. How could distant regions of the universe, seemingly never in communication, appear to have the same temperature, the same properties? And why does our universe seem to be so incredibly flat, so finely balanced between curving in on itself or expanding forever? These profound questions found their elegant explanation in a concept called cosmic inflation. Imagine a brief, extraordinarily rapid phase of accelerated expansion during the earliest, most fleeting moments of the universe, a cosmic growth spurt that ironed out any initial irregularities, making the universe vastly homogeneous and flat. It's a breathtaking idea, suggesting an initial burst of exponential growth that set the stage for all that followed. Through meticulous measurements of this ongoing expansion rate, using cosmic lighthouses like supernovae, scientists have been able to calculate the age of our universe with astonishing precision. We place this initial singularity, this moment of ultimate beginning, at an estimated 13.787 billion years ago, with a remarkably small margin of error. Think of it, nearly 14 billion years of cosmic evolution, from an infinitely dense point to the vast, complex, beautiful universe we inhabit today. This incredible span of time, far beyond human comprehension, humbles us and connects us to a story far larger than ourselves. The sheer weight of empirical evidence, gathered from telescopes both on Earth and in space, from particle accelerators to detailed sky surveys, overwhelmingly favors the Big Bang event. It is now the widely accepted scientific framework for understanding our cosmic origins, a testament to centuries of human inquiry and discovery. When we extrapolate this cosmic expansion backward in time, using the known laws of physics that govern our universe, our models paint a picture of an extraordinarily hot and dense primordial universe. It's a vision of intense energy, where matter and radiation were inextricably intertwined. However, as we push back to the very, very first sliver of a second, to the Planck epoch, our current physics begins to falter. The laws we know, particularly general relativity, struggle to describe conditions of such extreme density and temperature. This is where the frontiers of physics lie, where quantum gravity and new theories are sought to truly understand the very beginning, a realm of profound mystery and potential discovery. As the universe continued its inexorable expansion, it began to cool. This cooling was crucial, like a cosmic oven slowly turning down its heat, allowing for increasingly complex structures to emerge. First, the incredibly hot plasma cooled sufficiently for fundamental subatomic particles, quarks and gluons, to coalesce, then forming protons and neutrons. Further cooling permitted these protons and neutrons to fuse, giving rise to the nuclei of those primordial elements we discussed, mostly hydrogen, with significant amounts of helium, and trace amounts of lithium. It was a universe of simple constituents, yet pregnant with the potential for immense complexity. Then, over vast stretches of time, the subtle force of gravity began its patient work. These primordial elements, drawn together by their mutual gravitational attraction, aided profoundly by the invisible scaffolding of dark matter, a mysterious substance that provides extra gravitational pull without emitting or reflecting light, began to clump and gather. Slowly, painstakingly, these coalescing clouds of gas and dark matter grew denser, hotter, until conditions were ripe for the birth of the first stars. These stellar nurseries ignited, blazing forth, creating the first light in a universe that had previously been dark, apart from the CMB glow. Within these first generations of stars, heavier elements were forged in their fiery cores and explosive deaths, enriching the cosmos, providing the raw materials for planets, and eventually, for life itself. These stars then gathered into galaxies, forming the magnificent structures we observe across the cosmos today. And the story continues to unfold. Modern measurements, particularly those from observing distant supernovae, reveal an astonishing twist. The expansion of the universe is not merely ongoing, it's accelerating. This means that galaxies are not only moving away from each other, but the rate at which they recede is speeding up. This observation led to the concept of dark energy, a mysterious, pervasive force or property of space itself, that acts as a kind of anti-gravity, pushing the universe apart. It's a profound puzzle, a significant component of our universe that we are only just beginning to grapple with, a reminder that even with all our knowledge, the cosmos still holds deep secrets. This grand narrative didn't appear overnight. Its foundations were laid through the brilliant minds of individuals across decades. It was the physicist Alexander Friedmann in 1922 who first introduced the concept of an expanding universe through his elegant mathematical derivations of what are now known as the Friedmann equations. His work provided the theoretical framework. A few years later, in 1929, the empirical observations caught up, with physicist Edwin Hubble's groundbreaking work. Hubble discerned that galaxies were indeed moving away from Earth, and crucially, that their recession velocity was proportional to their distance, a relationship now famously known as Hubble's law. This was the first concrete observational evidence of an expanding universe. Independent of Friedmann's mathematics and Hubble's observations, in 1931, physicist Georges Lemaitre, a priest and a cosmologist, proposed that the universe emerged from a primeval atom, an incredibly dense and hot initial state. It was Lemaitre who truly introduced the modern notion of the Big Bang, long before it was given that slightly pejorative, yet now iconic, name by its detractors. His foresight was remarkable. The story gained even more profound weight in 1964 with the accidental discovery of the cosmic microwave background by Arno Penzias and Robert Wilson, who were troubleshooting a noisy antenna. They found this persistent, inexplicable background hum coming from every direction in the sky. Over the subsequent years, detailed measurements confirmed this radiation to be remarkably uniform, and its energy spectrum perfectly matched what physicists would expect from a universe that had cooled from an incredibly hot, dense state. This discovery was the ultimate smoking gun for the Big Bang. By the late 1960s, this overwhelming evidence led most cosmologists to conclude that the competing steady-state model of cosmic evolution, which proposed a universe with no beginning and a constant average density, was incorrect. The Big Bang had triumphed, not through dogma, but through the relentless pursuit of empirical evidence and theoretical consistency. Yet, even with this robust framework, there remain aspects of our observed universe that are not yet fully or adequately explained by current Big Bang models. These aren't flaws in the core theory, but rather exciting frontiers for future discovery. For instance, the unequal abundances of matter and antimatter, known as baryon asymmetry, is a profound puzzle. Why is there so much more matter than antimatter in our universe? If they are created in equal amounts, they should have annihilated each other, leaving behind only radiation. The fact that we exist means there was a tiny excess of matter, but the precise mechanism for this remains a mystery. Then there is the detailed nature of dark matter. While we know it plays a crucial role in forming galaxies and large-scale structures through its gravitational pull, we don't yet know what it is. It doesn't interact with light or other electromagnetic forces, making it incredibly elusive. We can infer its presence, but its fundamental nature remains one of the universe's greatest riddles. And of course, there's the origin of dark energy, that mysterious force accelerating the universe's expansion. Is it a property of space itself, a new fundamental field, or something else entirely? These unanswered questions are not signs of weakness but rather beacons guiding the next generation of scientists toward even deeper understanding. The Big Bang cosmological models, this magnificent intellectual construct, rests upon a few fundamental assumptions, postulates that have been rigorously tested and affirmed. One is the universality of physical laws. This seemingly simple idea is profound. It assumes that the laws of physics we observe and understand here on Earth, in our solar system, apply universally throughout the entire cosmos and have done so throughout cosmic history. It means that the force of gravity, the properties of light, the behavior of particles, these are consistent across billions of light years and billions of years. This universality is a cornerstone of the theory of relativity and has been tested through observations showing, for example, that fundamental constants like the fine structure constant have remained remarkably stable over the vast age of the universe. The general theory of relativity itself, the key physical law behind these models, has passed incredibly stringent tests, from the precise orbits of planets in our solar system to the dance of binary stars, proving its remarkable accuracy in describing gravity. Another crucial assumption is the cosmological principle. This elegant idea states that, on sufficiently large scales, the universe is homogeneous and isotropic. What does that mean? Homogeneous means that the universe appears roughly the same everywhere, regardless of your location within it. Isotropic means it appears the same in all directions, no matter which way you look. Imagine a vast ocean. From any ship, in any direction, it looks pretty much the same. Our universe, when viewed on scales larger than galaxy clusters, exhibits this astonishing uniformity. This principle isn't just a philosophical preference. It's been robustly confirmed through incredibly detailed observations of the cosmic microwave background radiation. The temperature of the CMB, that ancient light, is almost perfectly uniform across the sky, varying by only about 1 part in 100,000, a level of homogeneity that directly supports the cosmological principle to an astonishing degree. This uniformity, on the scale of the CMB horizon, suggests a universe that is indeed broadly the same everywhere. Finally, the models assume that the matter content of the universe can be broadly modeled as a perfect fluid. In physics, a perfect fluid is an idealized concept. It has no viscosity, meaning it offers no resistance to shear forces, and its pressure is directly proportional to its density. While the universe is certainly not a simple liquid, this approximation allows physicists to simplify the incredibly complex interactions of countless particles and forces into a manageable, effective description for the large-scale behavior of the cosmic fluid, enabling the mathematical modeling that underpins the Big Bang theory. These assumptions, initially taken as postulates, have been relentlessly scrutinized and tested by observations. And the remarkable thing is, they hold up. They allow us to simplify the incredibly complex equations of general relativity, leading to the Friedmann, Lemaitre, Robertson, Walker metric. This powerful mathematical tool describes the geometry of the universe, how it curves and unfolds, and when combined with the perfect fluid assumption, gives us the Friedmann equations. These equations are the heart of Big Bang cosmology, providing a mathematical description of how that geometry evolves over time. At this profound level of description, there's one incredibly powerful parameter: the mass-energy density of the universe. It is this density that dictates the very geometry of space and the pace of its expansion. The entire saga of the Big Bang, all its major features, from its initial expansion to its future fate, are direct consequences of this fundamental relationship between the universe's density and its evolving geometry. So, as we drift off into the quiet contemplation of these cosmic truths, let the vastness of this story gently wash over you. From an unimaginably dense beginning, through moments of fiery creation, to the slow, steady cooling that allowed atoms and then stars and galaxies to form, to the ongoing, accelerating expansion driven by mysterious dark energy. Our universe is a living, evolving entity. The Big Bang is not just a scientific theory, it's a profound narrative about origins, about the unfolding of potential into reality, about the deep interconnectedness of everything we see and feel. It reminds us of our infinitesimal yet deeply significant place within this grand cosmic ballet, born from the very dust of ancient stars, and connected to the fabric of spacetime itself. May this thought bring you a sense of peace, a quiet wonder, and a deep connection to the universe as you prepare for a restful sleep. Good night, dear listener.